Hello, welcome back to World Regional Geography, Chapter 1. This time we're talking about physical geography. And of course, whenever we talk about the physical geography of the Earth, we have to keep in mind that it's not by itself in the universe, let alone the solar system. So whenever we look at it, we can start by looking at how it relates to the sun and how that impacts our atmosphere. Conceptually, we're at a 23.5-degree angle whenever we're looking at the relationship between the Earth and the sun. That tilt allows the northern hemisphere to be closer to the sun in portions of the year, and the southern hemisphere to be closer to the sun in other parts of the year. Whenever it's summer in North America, then it's going to be winter in Australia and South America. Whenever it's summer in South America and Australia, it's going to be winter in North America and Europe. So we get this counterpoint of temperatures. So we get swings depending on which hemisphere, north and south, you're in as we go through the year. This explains our seasons. But what else is happening in our atmosphere? Well, our atmosphere is altered by the seasons, but it's also altered by other things. Proximity to the equator, proximity to the poles, conversely. And so whenever we're looking at these relationships in the atmosphere, as well as things like wind that's being created by the movement of the planet in the atmosphere, we're looking at the creation of two of our main concepts in terms of atmospheric impacts through the rest of the chapters, which are weather and climate. Weather you can think of as what's going on outside your window right now, or somebody's window. Climate is what you're planning for, what you've seen over time. So whenever we're looking at weather, it's the immediate state of temperature and precipitation in the area. Climate then is averages of those over time. We also have the idea of climate regions, and that means that we have certain areas where the climate is similar in these places over time. So these climate regions or systems can be things like rainforest or the polar regions, where we get the same type of weather over and over again over time. We can see a map of those here. This is the Köppen climate system map. And we get everything from darker redder colors, which are deserts and arid climates, so dry climates, hot climates, to the polar climates in the letters of E's, E, not E's, but E, where we're talking about areas that are very far north and very far south, so they're not getting as much energy overall. So we get most energy at the equator, even though we have a little bit of a tilt. The equator gets some kind of consistent amount of energy throughout the year, and the poles get the least. And of course, we see that there's changes between the equator and each of the poles, but there's also changes as we get further and closer to the oceans. So all of these different things have relationships that yield the climates that we have today. We also have the impact, and you saw that on the climate system map, where things are a little bit different in mountains. And that's because mountains very quickly change the distance from the surface of the Earth. And as we get further away from the surface of the Earth, we get to cooler temperatures. Also, because of that cooler temperature, that means that moisture that's being pushed across mountains cools. Wherever it cools, reaches the dew point, becomes precipitation, and falls. So we have these specialized climate systems for our taller mountains, like the Himalayas, the Andes, the Rockies in North America, that are different from the areas that are right around them because of the height that they provide. We also have the impact of orographic lifting. That's where we do have that moisture coming up, being pushed over mountains, going up higher, cooling and falling. So that's orographic lifting. Oro meaning mountain, graphic meaning terrain. So mountain terrain, lifting, or precipitation. As we look at long-term cycles, beyond just the climate systems, to look at long-term averages in climate, climate change has been going on since the planet began. We are actually cooler now than we have been, or were at least, millions of years ago. But in terms of the time since we've been here, especially looking at the last 10,000 years, temperatures have been much cooler, and we're beginning to see that upswing that we talk about in terms of global warming. So global warming is only talking about the last 150, 200 years. Whenever we look over the last couple of 100,000 years, we had not just ice ages, but generally cooler temperatures as well. We did see one spike around 5,000, 6,000 years ago. 8,000 years ago. Right after the ice age, but again, it was one that dipped back down after vegetation and things began to grow again. Whole sets of conversations that can be had about climate change, especially in terms of comparing the historic and prehistoric to the modern and expected. By the way, I didn't mention in any of the previous videos, but my background is as an archaeologist. So whenever I start talking about things that were happening a few thousand years ago, that's why. I have that focus on the prehistoric archaeologist who focuses around 7,000 to 8,000 years ago, as well as being a geographer. Whenever we look at things like global temperature change over the last couple of hundred years, again, that time that we're talking about, the anthropogenic global warming, we see that temperatures have risen on average around the world around 1.5 degrees Celsius. We're actually a little bit over that since this image was created a couple of years ago in 2016. Sorry, a few years ago in 2016. And we don't really see currently any real abatement to this warming process. And of course, you've heard a lot about ways that we can begin to slow this down. The fact that there are international treaties to try to do this. The U.S. has stepped away from the most recent, of course, but it's something that's a long-term goal, not just for those of us in the U.S., but around the world. We can also see that temperature change has not been consistent across the planet. So in the northern hemisphere, because there's more land, you get more heating because the land helps capture that energy. And it can heat up faster. Water tends to have a lower thermal inertia, so it warms up slower, but it does eventually warm up. So as you can see in this image, some of our highest temperature increases over the last few decades have been in the northern portions of the planet. You do see some warming around the South Pole, but again, it's through the northern hemisphere that we've really seen the most impact. And of course, it's also where we see the largest populations and the most generation of things like greenhouse gases in that portion of the world with the northern hemisphere. Here you can see one example from Alaska, images from 1941, where we have lots of ice sheet glacier throughout the area. 1950, where that glacier is beginning to recede, and we're beginning to see some of the water in that foreground that's part of the river. And then on the bottom, we see one from the 2000s where the glacier has receded even more. Not only do we see the river further into the image, but that foreground now has vegetation. So areas that were in permafrost, so vegetation couldn't grow in the first two images, the soil has thawed enough that we're actually getting firs and those type of vegetation in the foreground. So we can see then these impacts of climate change within the US itself. As we look at other aspects of the geography, we're moving from the atmosphere and its impact on things like ice sheets to the physical geography of the planet itself. Whenever we look at the geology, we're looking at the plate tectonics that make up the world. And to some extent, we actually use those as descriptors for the continents that we talk about in class. So North America, South America, Australia, Asia, these are largely based on the physical constructs, the plates beneath them, as well as the cultures that have developed there. And whenever we look at plate tectonics, we're looking at the movement of these plates both together, so converging in certain areas, apart, diverging, or transform, where they're kind of sliding against each other. Now, whenever we look at the Pacific Ocean, most of our plate boundaries, not all, but most of our plate boundaries are converging plate boundaries. This is where we get a lot of mountain building. This is where we get a lot of volcanoes. Because of this, the area around the Pacific Ocean is referred to as the Ring of Fire because of the volcanoes that basically litter or that circle around the Pacific Ocean. In the center of the Atlantic Ocean, we have a diverging plate boundary. So if you've ever seen images of Pangaea, where everything had come together 200 million years ago, it's that division between North America and South America and the rest of the world that's slowly opening up that has broken Pangaea up. And really, as North America and South America keep getting further and further away from Africa and Europe, we're seeing the shrinking really of the Pacific. Long term, millions of years before we see another mega continent again. But it doesn't mean that it's not having an impact on us on a daily basis. Everything from volcanoes and earthquakes to tsunamis whenever we have these type of events taking place under the ocean. So we can talk about the 2004 Indian Ocean tsunami. We can talk about the tsunami that was attached to the 2011 Japanese quake that had massive impacts on loss of life, first in the Indian Ocean as part of the 2004 quake, and then of course the east coast of Japan in 2011. So that's it for our conversation about physical geography. Next time we'll talk about human geography, and then we'll be able to move on to chapter 2 and get into the regions themselves.